Hey there, awesome physics students. I want to do another example problem with objects rolling down a ramp. And we're going to approach this again using rotational energy. So the basic scenario is, the two scenarios here are that we have an object that's a ring and a disk. And again, if you look at page 260 in your book, they have the moments of inertia for different objects. We're going to use the objects rolling, consider them the axis through the center of mass. Okay, and that's how we use this. So the ring has a moment of inertia that's mr squared, and the disk has a moment of inertia that's about half, that's exactly half of that. The reason for this, that the ring is so big, of course, all of its mass is on the edges here. So all of that mass is a distance r from the edge, and so of course the moment of inertia is just going to be m times the distance away from the axis squared, and that's going to be mr squared. For the disk, however, some of its mass is closer to the axis, but some of its mass is farther away. And when you do the calculation, the computation, which is an integral, I did this in a previous video, not for this shape, but for a different shape. When you do the integral needed, then you find that that averages between those two, and you get half mr squared, okay? So the moment of inertia for the disk is lower than the moment of inertia for the ring, because for the disk, it's more evenly spread out, whereas for the ring, it's all concentrated on the rim. All right, so let's roll these things down the ramp here and see what happens to them. So let's do the ring first. And the scenario that's often posed is if you put these two on a ramp and let them roll down, which one would reach the bottom first? So I think that you can probably come up with a prediction for which one reaches the bottom first based on just your understanding of what the moment of inertia means. So let me just remind you, the moment of inertia means resistance to changes in motion. And which of these has a higher resistance to changes in rotation? And of course, you probably noticed that it's this one because the moment of inertia is higher. So that suggests that the moment that the ring should have a lower velocity, a lower velocity when it reaches the bottom. And the disk should have a higher velocity when it reaches the bottom, because the acceleration for the disk will be larger. So let's see if that's true. So we'll do these in different, we'll do these conservation of energy for these, okay? Now, one simplification I'm going to make is I'm going to say that R is small compared to height, so I'm not going to add in the potential energy for the height of the ring here. And that won't matter. It actually doesn't matter anyway, but just forget about that. I'm going to gloss over that detail, at least right now. Okay, so let's write the energy for the ring. I'm going to use y equals 0, my 0 point for gravitational energy, potential energy. And so the gravitational potential, what we're saying here is the gravitational potential energy at the top gets converted into kinetic energy at the bottom. And we're going to say that's rotational kinetic energy. But it's not just rotational kinetic energy, because we want to find the velocity of the center of mass of this thing. So it's also going to be translational kinetic energy. Okay, so let's go ahead and set up our equation. Now that we know what energies are converted to what, we can write our equations that tell us that exactly precisely. So the gravitational potential energy for this should be mgh. And then that gets converted into rotational kinetic energy. So that's 1/2 I omega squared plus translational kinetic energy. And this is a I through the center of mass plus translational kinetic energy. So this is 1/2 mv of the center of mass squared. Okay, I'm going to drop, of course, this is all through the center of mass. So I'm just going to drop these two subscripts just so it's a little clearer. Remember that I for the ring is 1/2, mr squared. So let me go ahead and put that in, and I get 1/2. This is going to be mr squared omega squared plus 1/2 mv squared. Now you probably noticed that m is in every term here, so I can cancel that. And then there's one more thing I need to point out. This r omega here, this is r squared omega squared. Remember that let me just write it out, r omega by itself is going to be equal to v for rolling without slipping. Okay, so that is the center of mass velocity there. So I'm going to take advantage of that and plug that in there. So this r squared omega squared term here is actually v squared. So let me again write this down and simplify a little bit. So I get 1/2, this is v squared plus 1/2 v squared from this term. And that gives me v squared, just the whole thing. And then this, if I carry this down, that just becomes gh. And so this gives me, if I solve for this, this gives me v is equal to the square root of gh. Okay, fine. That's done. Now let's do it again for the disk. Okay, so we're still converting gravitational potential energy into rotational plus translational kinetic energy. So I'll write that out. And then let me put in for the moment of inertia there. So that's going to be 1/2 times 1/2 mr squared. And again, it's multiplied by omega squared. And we're going to do our same trick on that term that we did before. So that becomes, this becomes 1/4. And then this r squared omega squared becomes v squared. And then I add to that 1/2 mv squared from before. mgh. Again, I can cancel the masses here. I did it later. It doesn't matter when you do it, but you do need to do it eventually. And I can combine these. So this is 1/4 plus 1/2. That's 3/4. And that becomes 3/4 v squared equals gh. And so if I solve for v in this case, I multiply both sides by 4/3 and then take the square root, and that gives me 4/3 gh square root. Okay. Okay, so that's nice. Which is bigger? Well, this has a 1. There's an implicit 1 out front here, right? So let me compare this fraction here to this one. This would be 3/3, right? That's 1. Well, 3/3 is smaller than 4/3, and so this is bigger. And this is smaller. And so just as predicted, this one is this one has a larger center of mass velocity. Okay. And the reason for that, again, conceptually, is that it has less resistance to changes in motion, just because the moment of inertia is less. Okay. So hopefully this gives you an idea of how you approach these kinds of problems. We do it with the simple, we still, energy is energy, even if it's rotational or translational, and you can add them and you can mix them together. In this case, we had gravitational potential energy converted into both rotational kinetic energy and translational kinetic energy. Okay. Well, hopefully this was clear and that you understand how to incorporate rotational energy along with regular energy, and also gives you an insight about how you would think about different shapes, incorporating different shapes in different situations. So if you're trying to put wheels on a car, for example, where do you try to put the mass? In some cases, it's dictated by not what you would like to do for rotational inertia purposes, but just where does the net mass need to be in order to hold the things that you need. So for a car tire, for example, you need most of the mass at the end because that's where the tire is, and you can put it in the center, but you need some strength at the end too, so the tire doesn't, you can't be made of aluminum foil at the end of the rim. All right, that's enough rambling. I'll talk to you guys later. Bye.